In this video, we're going to talk about modified Atwood machines. So here is an example. Of a toy. Now to the math. Hi, this is Keely again, and let's talk about the modified Atwood machine. This one's a little different where on a regular Atwood machine, both masses are kind of hanging down. But this one, we actually have one mass on a horizontal surface while another mass is hanging off the edge from a pulley or something similar. And so, let's take a look at this one. Well, we got one block M1 that's 4 kilograms. I'm going to go ahead and write that in. 4. There's negligible friction between the table and the block. Good. That makes it easier. The string has negligible mass. Really good. That way we don't have to use calculus or anything like that. And M2 is 3 kilograms. There we go. And we want to know the acceleration of the system and the tension in the rope. And I always like to find the tension right there. So first, let's take a look at the free body diagram. So on this, we have the weight of this one pulling down, FG2, the tension in the rope, tension in the rope pulling this way. These two should be the same length because they're the same rope. We have gravity, or the weight, I should say, of M1, the normal force on M1, and since there's no friction, we don't have to worry about any resistance there. So that's our free body diagram. Remember, these two are about the same, or should be the same length. And we want to find the acceleration of the system. Now, there is a way to do this using these free body diagrams, and it's excellent. It just confuses me. So I've got this method that I like to use. It basically works like this. We're going to say the force that's making this move equals the force on the system. Okay, so what's making it move is the weight of this one. That's dragging everything over. So that's M2G. No resistance, so we don't have to worry about anything else. And the system is both masses put together, M1 plus M2 at some acceleration. Well, now that we got things figured out about what's happening with the system, let's plug in the numbers, see what we get. So M2 is 3, gravity's 9.8, M1 is 4, M2 is 3, some acceleration. So 3 times 9.8, 29.4 equals 4, 5, 6, 7, 7a. Divide by 7, we get an acceleration of 4.2 meters per second squared. Now, if I want to find the tension in that rope or string or whatever you want to call it, again, I like to doing this. I'm like, okay, I want to figure out how much this is pulling. I want to ignore this. I just want to know what this rope is doing to that mass. Nothing else. Simplify things up. And so we can do MA equals the sum of the forces. Well, there's no friction, so the only force acting that's causing it to move is that tension. So we have MA equals the tension. Well, the mass of that block is 4. The acceleration is 4.2. And whatever that is the tension in that rope. So my tension is 16.8 newtons, and that is it. All right, what if we add some friction into this? So let's say we've got two blocks, 6 kilograms and 4 kilograms, and the string is negligible interference from the pulley. There is friction this time. So the coefficient of friction is 0.2, and I've already got the free body diagram drawn where we have the weight of this one and the tension pulling here. These two are the same. The weight of the block on the table and the normal force because it is touching a surface. Then a little bit of friction right there. And we have to figure out what is the acceleration of this system. Well, since there is friction, I want to go ahead and figure that out first, because that's a level surface, and we know that the normal force and the weight of the object should be the same, because this string is pulling perfectly horizontal. It's not lifting it or dragging it down. So the normal force is mass times gravity, which for that block, so 6 times 9.8. And so the normal force is 58.8 newtons. All right. I'm just going to hold on to that. And we're going to figure out the acceleration. And I want to go back and use this system that I really like, where the force that's causing it to move equals the force on the system. What's making it move, or affecting the motion, I should say, is the weight of this one, but friction is holding it back on that one. So we're going to have the weight of this one minus the force of friction on the object equals the system, which is still M1 plus M2 times that A that we got to figure out. And so we get M2G equal, minus mu times the normal force, which we figured that out, equals M1 plus M2A. Now we can drop our numbers in. 4 times 9.8 minus 0.2 times 58.8 equals 4 plus 6A. And now we just throw it into a calculator. Minus 0.2 times 58.8 divided by 10. A equals 2.74 meters per second squared. So that's the acceleration of the system. What's the tension in the string? Well, that's going to be new, because now we got friction. And so, again, we're going to ignore this and just think about what's happening to that string. That string is pulling this block, and it's got friction on it. So we got MA equals the sum of the forces. In this case, we got MA equals tension minus friction. So the mass is 6, acceleration is 2.74. Tension we don't know, but friction was whatever that was. So I'll write it down again, 0.2 times 58.8. $16.44 minus 11.76. That's going to be added when we put over to the other side, so it's going to be plus 16.44. We get a tension of 28.2 newtons, because the first 11.76 is just going into defeating friction. Then the rest of it is actually what's causing it to accelerate across the table. So let's make it a little bit more complicated. So we got 3 blocks now, 2 on the table, 1 hanging off the edge. And let's start off with a free body diagram. So block 3 has the most weight. They all actually have weight, just depending on how much their mass is. So that's the smallest, that one's bigger, that one's the biggest. Just going by the masses. And we have a tension. These two are the same, so they should be the same length. This tension should be slightly less, because this rope is only moving that block, not the whole thing. So I'm going to call these 1s, and that's a T2. They have friction. Again, 1's going to be a little bit smaller than the friction on 2, because it has less mass. And then we have normal forces on both these. Corresponding to their weights. So this one should be slightly bigger than that one, although looks like in my picture I actually drew that one bigger. But anyway. So what are we going to do with this one? So we got to figure out some friction forces. And again, so this is a horizontal table. So we can do this. We can say that the normal force is equal to the weight of that object. Okay. So the friction force on one will be equal to mu times the weight of m1. So it's mass 1 and gravity. Friction on 2 will be equal to mu mass 2 times gravity, because it's the weight of that one. And if you want, we can go ahead and just calculate those. Why not? So that's 0.25. Mass is 4. Gravity is 9.8. So we get 4 times 0.25. Wait, guess what? That's 1 times 9.8. So this is 9.8 newtons of friction for that first one. This one's going to be 0.25. Mass of that one is 5. Gravity is 9.8. So 0.25 times 5 times 9.8 gives me 12.25 newtons for the friction force on the second block. I'm just going to keep those in my pocket right there. And so I can, there we go, so you can see them. I just want to keep those in my pocket right there so I can use them later. I want to start off by working on our acceleration. So what's making this move? Because we got to do force that's affecting the motion equals the force on the system. Okay, what's making it move is the weight of this one, but the friction force of these two is holding it back. So we have m3g minus force of friction on 1 minus force of friction on 2 equals, the system is all three masses together, so m1 plus m2 plus m3 times A. Now we got our equation set up. And so we can actually start throwing some numbers in. So that's going to be 6 times 9.8 minus 9.8 minus 12.25 equals 4 plus 5 plus 6a. And now we just start working on the mass. So 6 times 9.8 gives me that minus 9.8 minus 12.25. This side over here is 36.75. We've got 15a, so we're going to divide by 15. We get an acceleration of 2.45 meters per second squared. Now we can figure out how much tension is in each rope. And we're going to start off with, let's start off with A. Cover up everything. Just look at what A is doing. A is moving that block. Okay? A is just moving that block. So if I want to figure out the force or the tension in that one, I want to do MA equals the sum of the forces. So MA equals tension minus the force of friction on that one. So we're talking about 1. So the mass of 1 is 4. Its acceleration is 2.45. Because everything's going to be accelerating at the same rate because they're all tied together with the same rope. Tension we don't know. Friction we just calculated over here. It's 9.8. So we can figure out the tension in A. Let's put a little A there. Let's figure out the tension. So we got 4 times 2.45 gives me that. We're going to add 9.8 to both sides. So we're going to add another 9.8 to it. And so the tension at point A is 19.6 newtons. Now for the tension at B. Now B, that rope is pulling that one, which is also pulling this one. So B is actually moving both these masses. So we still have MA equals the sum of the forces. And as far as that rope right there at B knows, it's just moving one block that has the combined mass of both M1 and M2. So we've got M1 plus M2 A equals the tension at B minus the friction for both these. So we got the friction force for one minus the friction force of two. We've got all those things going on there. So let's go ahead and plug our numbers in. So we've got 4 plus 5 times 2.45 equals the tension that we're looking for minus, we figured these all out in advance. So that's 9.8 minus another 12.25. And so we'll start figuring this out. So 9 times 2.45 gives me 20.05. Those together, 9.8 plus 12.25 means we're going to be 22.05. Wow, that's unusual. And so we're going to add that to the other side. So plus 20.05. And we get the tension in B to be 42.1 newtons. Which makes sense. It should have more tension in it because it's got to pull both these masses, while A only has to pull that mass. And there we go. That's how you do some Atwood machines. Now I've got one more thing I want to show you. Some hints and tips sometimes. Sometimes you might get a problem like this, where we've got something set up, pulley coming over, mass over here, but let's say we've got a rope and this is tied to a wall. Or it may be just where it is being held still by something. So it doesn't have to be a wall. Maybe it's just at rest. But anyway, it's not moving, it's not acceleration. That means that then the tension in this rope has got to be equal to the weight of this mass coming off the end. Because since it's not accelerating, what this rope is doing is actually holding up this mass. And so the tension will automatically be equal to the weight of the mass that's hanging off the edge. Now when it's accelerating, that's when we have to do what we just got finished completing. But that's just a little tip, just in case that situation comes around. Thank you, and tune in later for some more videos. Goodbye.